So for this next to last video in chapter 2, I'm going to go over the periodic table as well as introduce the mole concept. And in the last video, which will be the video after this, I'm going to do a challenge problem that shows the differences between ions and understanding, or not, excuse me, not ions, but isotopes. So let's take a look at the periodic table. The periodic table is kind of broken up into different sections. The first thing that we can kind of break it up by is this stair step. Okay. Anything that's on the right-hand side is a nonmetal. Anything on the left-hand side is a metal. Except hydrogen. Hydrogen is a nonmetal, unless you compress it. Right? The periodic table is all based on essentially room temperature. These things that are next to the that stair step in green are called metalloids. We can also break down the periodic table into periods and groups. Periods are rows on the periodic table. Groups are columns. They're also known as families. We break your main group elements into the, I'll do it in red, the first two columns and the last six. These are main group elements, also known as group A elements. The stuff in the middle are known as transition metals, or transition elements, or B elements. We have special names that we call certain periods, or excuse me, not certain periods, but certain families. This first group, right, first family, is known as the alkali metals. By the way, I should mention that the reason why we call them families is because anything in a column shares similar properties and reactivity mostly. This second column here of the group A elements is known as the alkaline earth metals. Group 7A over here, or 17 if you're using the IUPAC table, is known as the halogens. And group 8A is known as the noble gases. They're known as noble gases because they do not react. In fact, you have to get all the way down to xenon before they will start doing covalent bonds. As I said, group 1A is also known as the alkali metals. Group 2A is the alkaline earth metals. Group 7A is the halogens. And group 8A is the noble gases. And the reason why we break up the periodic table by metals and nonmetals is because it tells us a little bit about the elements. Metals are conductive. This is due to what's called the sea of electrons that's around them. We'll talk more about that, and as well as specific heat. The melting points are fairly high. They can be, it's very dependent, but for the most part they're pretty high. That's why they're solids at room temperature. They're ductile, which means they can be stretched. They're lustrous, which means they shine. You'll talk a little bit about that in 1B, why they do that. They're malleable, which means they can be hammered into shapes. Conversely, nonmetals are poor conductors. Their melting points are all over the place. Some of them are gases at room temperatures. Other are very, very, very high melting points. But in general, they're brittle and dull. They break easily, they fracture, and they have no luster. Metalloids are somewhere in between. So for example, silicon is a metalloid, and it acts as a semiconductor. It kind of conducts, but not nearly as much as a metal does. So the last thing I want to bring up in this video before I do the challenge problem in the next video is the mole. So I don't. I guess I had problems with it whenever I was a student too, but after I got used to it, the mole concept just seems like anything else that you get used to in life, right? It just makes sense. So in 12 grams of carbon, okay, you have 6.02 times 10 to the 23rd atoms of carbon. What does that look like? Okay, well, so 6.02 times 10 to the 23rd. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh, I went one too many. 23. Okay, so right here is the population of the world. More commas, more commas. Wow. Right? That's a lot. And that's just in 12 grams. Think of how many atoms there are in the Earth or in all of the planets or in a star, right? These numbers are just this gigantic numbers that are just too unfathomable for us to understand. Okay? It's impossible. There are more atoms in a mole of an element than there are stars in the sky. That's crazy, right? When we think of the vastness of the universe. All right, so I'll stop waxing philosophical and let's kind of put this into perspective. I like to think of the mole concept as a dozen, right? So I can buy a dozen roses for my wife. I could buy a dozen donuts for myself. I could buy 2 dozen donuts and have one for my wife and one for myself, right? I could have a dozen cats if I wanted to. I could have a dozen cars. The dozen doesn't matter what it's attached to. It's 12. And we use that in order to kind of simplify things, right? Instead of saying, hi, I would like 12 roses. You just say, I want a dozen roses, you know? Instead of saying, I want 5 dozen, what would that be? 60 roses. I want 5 dozen, right? It just makes it easier. And it's the same thing with the mole concept. 1 mole is just 6.022 times 10 to the 23rd of whatever we're dealing with. It doesn't matter what it is. It could be a mole of carbon atoms. It could be a mole of oxygen molecules. It could be a mole of cats. So it's just a number, and it's just an amount. It's like saying, you could say that I have 1,000,000 right? And everybody's like, okay, whatever you say, buddy. But if you say you have $1 million, it's understand. It's just a number that goes along with it, and it's a ratio. It's 1 mole is equal to 6.022 times 10 to the 23 of whatever. And we're going to find out why the mole is so useful here in a minute. So let's look at a couple of examples of how big a mole is. I like this one. This is my favorite. Okay. So a stack of paper with 6 times 10 to the 23rd sheets would be so tall that it would reach from here to the sun. Not once, but more than 1,000,000 times going back and forth. That's insane. It takes 8 minutes for light to reach us from the sun. That goes at 2.9979 times 10 to the 8th meters per second. So it's just a big, big number. It's hard to digest what it is. But why do we use it? Well, we're going to find out in chapter 3 that it's very useful to put things in terms of moles because that's what's on the periodic table. Also, because it's a counted number, we can use it instead of atoms. We can use moles for reactions. So moles are just ratios. 6.022 times 10 to the 23rd, whatever, like I wrote up there, per 1 mole of whatever. So let's try it out. Osmium is the densest naturally occurring element with a density of 22.59 grams per centimeters cubed. How many atoms are in a cube of osmium? That is 1.00 millimeters on edge. So we're going to have to introduce something that we're not quite ready to talk about. It's in chapter 3, but you should be familiar with it from Chem 4, molar mass. Molar mass effectively says that for every, right, we talked about this already, that if I look at osmium, the average mass of any given osmium atom is going to be 190.23. So, right, and it's going to differ based on different isotopes. Well, we can scale this up because this is per atom. That's kind of useless to us. What we could do instead is say 190.23 grams per mole. And so the number on the periodic table effectively tells us gram per mole, and it's a ratio that we can use. So I have 1.00 millimeters, and I need to cube it. Well, that was easy. Let's start doing some dimensional analysis. So 1.00 millimeters cubed. I need to get the centimeters cubed. So for every 10 millimeters, I have 1 centimeter. I need to cube that whole thing. And then for every 1 cubic centimeter, I have 22.59 grams. Now I can go to molar mass. So for every 190.23 grams, I have 1 mole of osmium. And then for every 1 mole of osmium, I have 6.022 times 10 to the 23rd atoms of osmium. Multiply across the top, divide by the bottom, and I end up getting 7.15 times 10 to the 19 atoms. Get used to this. Okay, we're going to use it a lot. In the next problem, I'm going to demonstrate what's called a challenge problem. It's a difficult problem that kind of brings a lot of the things that we've been talking to perspective.